Welcome to part 2 of sign multiplication video. As I promised, I'm going to show you an example or two examples how we can multiply these numbers. I showed you the major difference between sign and unsigned multiplication. This was unsigned, this is sign. Key steps are okay. The key differences, are the sign extension here during partial products generation. Then when you add up everything, the last partial product, since it's a sign bit, you need to take a 2's complement of that and then add to the rest. So those are the two differences. You will understand it once we go through an example. Actually, I'm taking exactly same example here, but this time actually calculating these two. So first look into this part only. Okay, I just can't make it this thing. Oh, I can. Okay, 1 second. Yeah, it will not look good. So anyway, focus on this part. And the differences are over here. We'll go in a minute. So this is same number, which was, what was it? 13? Yeah, 14, 13. So 14, 13, no sign bit. Okay. Why I didn't put a number here? Okay, let's do this. This is first number, this is second number, and first step is to generate partial product 1, then partial product 2, and then create a S1, this thing. So create S1. For that you need partial product 1 and 2. How you create partial product 1? You already know it, but let me explain it. You multiply 1 with this entire multiplicand. So what happens? The whole multiplicand comes down. These pink zeros that you see, these means the number is only 4 bit, but total in the final product we will have 8 bits. So what we do is, since it's unsigned number, just put 0 there. So we haven't extended this one. It's just 0. Partial products 2 is all 0 because the second number we are multiplying is 0. So anything multiplied with 0 is 0. So whole thing becomes 0. Third partial product is 1. For fourth partial product, we also have 1 in the multiplier. So just remember that because I'm going down now. I might write that because this was multiplication with, it doesn't write outside. Okay, 1 second. Which color we pick? We pick red. This was multiplication with 1. This multiplication is 0. This is multiplication 1. And this is multiplication with 1. Okay, just for you to remember that. And our multiplicand is this. Just remember that. Okay, we already discussed. Let's add them. 0, 1, 0, 1, 0, 1, 1, 0, 1. And second partial product starts from here because its weight is 2. And you can see that we had to extend, sorry, not extending, we had to put 0 on the 3 most significant bits. And here 4. Then add them, we get this, S1. Now partial product number 3, you have to multiply 1 with the multiplicand. So the whole multiplicand comes down, but it starts further shift. First, second, third partial product start here. Again, in order to make it 8, you put 0 at the 2 most significant bits. Leave this one, but these are 0. Yeah, 0, 0, 0, 0, 0. Oops. All right. So you got that? Okay. Then multiply by 1. This is partial product 3. Add it to 0. Now, in order to calculate sum 2, you add S1 to partial product 3. Just like our equations over here. So 0, 0, 1, 0, 1, 1, 1, 1, 1, 0. You goes 1 as carry. then 1 plus 0 plus 1 is 0, 1 is carry, 1 1 0 and carry. We missed the carry. Okay, let's do that again. 0 0 0 1 0 1 1 0 1 1 1 0 1 1 1 0 1 1 1 0 1, then 1 and 0. Somehow I put this number correct, but there was no carry. All right. Anyway, as partial product number 4, since you're multiplying 1 with multiplicand, the whole thing comes down, but you start it from here because this is the last bit with 8. You just have to add one more 0 to it. Now add S2 and partial product 4. So 0 0 1 0 1 1 0 1 0 1 1 1 1 0. Carry goes here and then 1 0 1. Now you need to figure out this is 1 2 3 4 5 6 7 8 bits. Weight is 2 raised to power 0. 1 2 3 4 5 6 7. 2 raised to power 7 is the weight, but this is positive weight. Now weight we have 1 here. 2 raised to power 7, 2 raised to power 5, 2 to the power 4, 2 2 2 1, and you get 2 to 7 is 128, 32, 16, 4, 2, and you add them, it becomes 182. I already calculated that, which matches our original multiplication. Now let's look into sign multiplication. Again, we have two numbers. One is this, one is that, but again, those are 4 bits, but the most significant bits is a sign bit. So we can put much smaller number in the same 4 bits because we don't have this weight of plus 8, we have minus 8. So when minus is added to the plus, number becomes smaller. Let's multiply this. This is partial product 1. And here is the difference. Partial product 1, it was 0, 1, 1, 1. So 0, 1, 1, 1. But this pink part is different. We put zeros there, but now we're putting 1. Why? Because the most significant bit was a sign bit. It has a negative weight. So in order for the 8-bit number to make sense, you need to extend it to all these locations. Second partial product 0, and we need to add 3 more zeros here. Since most significant bit is 0, we just extend that. Same thing, sum 1 we added. Last time we didn't have negative numbers, so we are adding now 0 0 0. By the way, this is 0, this is 0, this is 0. So 0 0 0 1 0 1 1 0 1 1 0 1 1 0 1 1 0 1 1 1. Except this 0, everything is 1. This is our sum 1. Partial product 3 is, if you look at unsigned, 0 starts from here, 1 1 1. 0 start here, 1 1 1. We need to make 8 bits. The last 2 bits, we just extend the sign this into this, into this. Sum 2, you just add them, 0 1 1 1 1 0 1 carry 1 1 1 is 1 1 carry 1 1 1 1 carry 1 1 1. This last carry you discard it because we have only 8 bits. Partial product 4 by default is 0 1 1 1 0 1 1 1, and you have to extend it by 1. This sign goes this. We need to create 2's complement of this. Oops. So what we do here is, in order to create 2's complement, this one we created 1's complement first, which is basically flipping every bit, and then you add 1 to 1's complement. So you add 1 1 1 0, carry out 1 1 0 1 0 0 0. So this is the partial product number 4 with 2's complement, so negative of it, and this is without 2's complement. Since it's a negative bit, so we have to calculate that. If it was 0, then everything will be 0. You understand that's the key impact. So what we calculate as 3 is the difference between this and this is you still have s2 even though it's sign extended, and then you add 2's complement or partial product 4. So we have partial product 4, right? And then we have s2. So we have s2 and partial product 4, so we get s3 but simply adding them. So let's add them. So this is 0 0 0, so simply 0 1 1 0 1 1 0 1 carry 1 1 0 1 carry 1 1 0 1 carry 1 1 0 1 carry. With this is the carry we discarded. We have only 5 bits. So let's look into that. Everything is 0. Excuse me. This is negative 8, but it's 0. And the only ones we have at these two positions, this is 4, this is 2. So when you add them together, 6. And as expected, when you multiply -2 and -3 is 6. So practice the same example that I did one more time, but just watching the video you will not understand. And just do a few more practices. Just pick some numbers and see if you face any difficulty. If yes, just let me know. Now comes to the hardware implementation of it. This is what I had during unsigned case. And this was the array multiplier. I also call it parallel multiplier. Then there was a separate video I did for unsigned number, which was a serial multiplier, which I had only one full adder, as in the case of one ALU, one core, and just use an algorithm to bring every time shift numbers and bring them, and eventually we found that that algorithm was working. In the signed case, the same thing. This is the array multiplier, but this is the unsigned one. So now think about it. In the unsigned case, we had in the unsigned case we have zeros here, so no need to add those things. So if you remember how many half adder and full adder we used, and each time this full adder, there's a partial product. So what happens, this comes here, this partial product bit comes here, sum generated comes down, carry out goes into the next full adder, then bit come here, full adder, sum comes down for the next stage, and the carry out. Well, in this case, now I use half adder because I didn't have anything. But in the case of a signed multiplication number, you have 1 here. So it's not something you can ignore. So carry out goes here, and that numbers come here. And it becomes a full adder because it can be 0 or 1. Then you do this bit, and you cannot assume there's nothing there. There is 1 or 0 depending upon whatever the value is. So you need an again full adder. So full adders. So in all these cases, and you go to the next line, you don't have any full adder, but in this case you will have full adder. So just to give you an idea, I'm not going to implement all that, but it will result in more full adders. You will have a complete filling here. You just can't assume like 0 before. However, luckily, I'm not going into detail. There are ways that you can simplify them and avoid them. Actually, I will give a link of a YouTube video. They discusses when you add one here, and how you can get rid of extra full adders there and just think it's 0 here. So there are techniques there. Similarly, on the serial multiplication side for sign, there are some algorithms, but those algorithms, some more if else, some more shifting, some more checking, more control logic. So it becomes a bigger digital system on its own. But the overall theme that you are getting here is that multiplication is not easy. It takes a lot of resources, or it takes a lot of time. In this case, a lot of resources. in the serial case a lot of time. You keep shifting things. Multiplication, addition, like the accumulation operation, are a very important part of deep neural network and other lot of image, video processing or signal processing algorithms. And coming up with the right architecture for that is super important. So I'm gonna stop this video here and actually stop the topic of multipliers. Maybe later on, if we create the chip that I plan to design, if we have some structures where we need to optimize multiplier, then we will address more optimization within that. But so far in this logic design course, my goal is to give you an idea of how you can build different digital systems, starting with a smaller one and then complicate them over time and make them bigger over time. And then we get into physical design, another part of RTL design, and then you will see how we actually use those. So that's it for now, and that's all for the multipliers. Next video, I will get into division and see how we can implement that. And after that, we have some shift left and shift right architecture, how we can implement that. And with that, most likely we will conclude combinational circuits. Thank you so much for watching. Thanks for your time. If you have any comments, if there are anything that you suggest me to improve, you can contact me on LinkedIn. Really appreciate your time once again. Take care. Bye.